Well, welcome to this lesson on the HC-SR04 Ultrasonic distance sensor. For something that has such a long name and number, these items are very, very common. You'll find them in just about every robot car that has the ability to move around obstacles, and I certainly got my first couple of these in some basic Arduino kits that I bought. They're sort of one of the standard items that they put in there. Now, what these sensors basically do is they send out a pulse of sound at ultrasonic frequencies. That's above the type of sound that we as humans can hear. Just be aware though that your cat, dog, mice or other small animals can actually hear those frequencies. So if you're going to be firing this thing constantly, try not to point it at animals. Let's try and be nice to them. They are actually used, it's a similar system that's used in gardens as an ultrasonic deterrent for cats. So in that situation, obviously the cat can run away from the noise, but just be aware if you're in a small room or you've got a sort of your pet hamster on your desk next to you, probably not a great thing if you're firing at the poor animal all day long. He's not going to have a good day. So that sort of safety tip aside, let's have a think about what this sensor does. Well, as I said, it sends out a pulse of sound, and what it basically does is it sends out the pulse and then measures the time that it takes for the echo to come back. So if you were to walk under a bridge and clap, obviously you hear an echo. With these sensors, they're tending to work at much shorter distances, so thankfully the electronics are up to the job of measuring very, very small time periods. So that's basically how the sensor works. It has a range technically from about 20 millimeters, 2 centimeters, up to 4,000 millimeters, about 4 meters. Now, I've done a few tests on mine, and it's true that I can get it to read down to 2 centimeters, 20 millimeters. However, if you're using this for a robot car, just a little tip, once the distance from your sensor gets less than 20 millimeters, bizarrely the distance suddenly increases. And I think that's because the sound comes off of the unit, bounces off my hand, bounces back off the front of the unit, back onto my hand, and back into the receiver unit. So all of a sudden your distance can increase. So if you're building a robot car, you really don't want it to start reacting when you get down to 20 millimeters, because just the momentum of the vehicle moving, it's going to keep going for at least another 10 millimeters, and by that time it's going to think that it's further away from the item than it was. So it may well accelerate. So these are little things that you have to think about with components like this. If you're doing an obstacle avoidance car, you need to start thinking about, well, let's shut this down at about 50 millimeters. And this is why these units, they're very similar to the units that you'll see in the back of a lot of cars. There's another sensor in this family. It's called a JSN-SR04T, and it's a very similar unit, except it's waterproof. And if you have a quick look on the web, there's a link to one on the Digital Town website, and you'll see they're the sort of thing that you see in car bumpers. And it's why when you're reversing in a car, it doesn't sort of go to zero. You always get a little bit of a gap, and it's that similar thing, making sure that the bounce comes back at the right time before you hear the crunch. So these sensors, what else have we got to say about them? Maximum range. It's supposed to be 4 meters, and it probably is. Difficult to tell in my office, on my workbench, because I've got it firing up at the ceiling, and that's about 1.5 meters away, 1,500 millimeters. But the issue that you can face is that the longer the distance you're trying to get a reflection of, in many ways the bigger item you need to reflect off of. I think I'd get a good signal at 4 meters if I fired this thing at a wall, but what you'll find is that if you move your hand in front of the sensor, it becomes more and more difficult to keep your hand at the center of the sensor. And that's again something to think about as if you're building an obstacle avoidance car, because you need to think about things like table legs and chair legs. They're not particularly wide, so I'm not sure you're going to get a particularly good hit on one of those if it's at sort of 2.5 meters away. Again, something to think about with your code. So today's lesson, we are going to start off by writing a basic sketch to control this sensor with an Arduino. Then what we're going to do is turn the sketch into a function. This is because it then becomes easier to move that function from one sketch to another. It just means you'll have a piece of portable code that's very, very easy to integrate with other sketches that you might have. Then what we're going to do is control multiple sensors, and they're all going to be firing at different times using different milli timers, just as an example of how to do that sort of thing. And then there'll be a final sketch, sketch 4, which will again use 3 sensors, but this time it's going to be firing them in a specific order. And it's the sort of thing that you would do if you'd built a car and you had a number of sensors on it pointing in different directions, maybe one straight ahead, one to the left, one to the right, the sort of way that you would read off of these sensors in order. So that's the plans for today's lesson. So let's get the IDE open and get started. So I've already loaded up the sketch to make things a little bit faster, and let's just start to work through this sketch. So the first thing, we're going to connect to the trigger pin, which is going to be pin 7, and we're going to have the echo pin, which is pin 6. Now if you go to the Digital Town website, you'll see that I've done a couple of wiring diagrams. One of them on the left is using a sensor shield, because if you're doing the robot car tutorial, you'll tend to be connecting to the sensor shield. The one on the right, obviously, I've just connected straight to the Arduino. Now if you look on the front of your sensor, you'll see that they're labeled VCC 5 volts, trigger, which is going to go to pin 7, echo, which is going to go to pin 6, and ground, which is going to go to ground. And the way this thing works is it sends a trigger, so we send a pulse to the unit to say, now we want a reading from you. As soon as that pin has gone high for a very short period of time, it will send out a sound pulse. The sound pulse will then be bounced back, and the echo pin basically does a clever little bit of timing and sends some results back to us, and we use a function that we'll look at called pulse later on in the sketch that actually works out all the timing for us. So those are your circuit diagrams. Now let's get on with the code again. So we've defined our pins, and then we've got 2 global variables. The first is an unsigned long, which is the duration. This is because the duration on this thing is working in very small periods of time, sort of down almost in your microseconds. So it's going to generate very, very big numbers very quickly. And then we've got an integer for the distance, which in my calculations is going to work out the distances in millimeters. Many of the sketches you'll see work out the distance in centimeters, but I wanted something just a little bit more accurate for later on in the robot car project. So those are the variables that we have. Now if we come down to the setup, we've got the usual serial, just so that we've got it started and we know that it's working. Then we've got the pin mode. So for the trigger pin, our pin mode is an output, because we will be sending the pin high or low when we want the unit to actually fire a pulse. And then if you'll notice, the pin mode for the echo pin is an input. So this will in turn receive a high or a low. And if you remember from previous lessons, high is basically 5 volts. Sometimes it's slightly different depending on the board you're on and the component, but it's a positive voltage, whereas low is 0 volts. So that's how the system is set up, and then we'll come down to the main loop and see how the code works. So for this sensor to work, what it needs is for the trigger pin to be active for 10 microseconds. That's not milliseconds, that's microseconds, that's millionths of a second. Now, to make sure that it knows what it's doing, what we do first is we have a delay, but a delay microseconds. Now, we'll have used normal delay before, which works in milliseconds, but there is also a function called delay microseconds, and what we're going to do is we're going to take the pin low for 2 millionths of a second. That's an absolutely minute period of time, but it ensures that the pin has gone low. It's one of these things that sometimes we need to check when we're programming. You know, what did we do? What was the pin doing last time it was used? Did I accidentally leave it high? This, if you like, is a bit of a safety belt. We're going to definitely put the pin low. So then we're going to trigger the pin high. So trigger pin will go high, go to plus 5 volts. And then what we do is we delay. But we do a delay in microseconds. So 10 microseconds. That is 10 millionths of a second. That's absolutely minute when you think it takes about 350 microseconds or something to blink, something like that, maybe even more. Then once we've sent the pin high for 10 microseconds, which will trigger the unit to send its sound pulse out, we're then going to take the pin low. So it's now ready for the next pulse. And then what we do is we use a function called pulse in. And this works on the echo pin. And what it does is it waits for the pin to go high. And then basically it starts the timer until the pin goes low. And that time is the time in microseconds, millionths of a second, that it took for the sound to go out from the unit and to return to it. Now, one of the great things about sound is that it basically is pretty constant. It's sound at sort of ground level moves at about 342 meters per second. It varies very, very slightly according to temperature, humidity, and a few other bits and pieces. But for our purposes, what we're going to do is we're going to take the duration, then we're going to multiply it by 0.34. That will give us the total distance in millimeters from that the pulse traveled. And then what we do is we divide it by 2. Because don't forget, the pulse went out from the unit, it hit the object, and then it bounced back. So the time that we're recording is the time that it took to the took to go to the object and come back. Obviously, we only want the distance to the object, so we divide the time by 2. And then all we're doing, quite simply, is we're going to print out some information, and basically, the important bit, we're going to tell ourselves the distance away from the sensor in millimeters. Now, if you look over on my COM port, I've already got the sketch running, and there's a delay in here. It only triggers once a second. Again, if I had a pet in the room, I'm sure the pet would appreciate the fact that I'm not firing this thing endlessly. But as you can see, the distance is there. They're staying pretty constant. There is some variation, not quite sure why. My ceiling is not moving, which I assume it's bouncing off the ceiling. And what I'll do now is just move my hand into its path, and you can see the distance changes. I move my hand away, the distance increases. I move my hand up close, the distance decreases. Now what I'm going to do is keep decreasing the distance and as I go down you see 29, 24, 22, oh, suddenly it's gone up. And it's that bit, as I've got my fingers virtually on the sensor, it's giving a higher reading, and that's because the pulse is bouncing all over the place before it gets to the receiver unit. Another little experiment, I've now moved my hand away, and at the moment I've got the palm of my hand pointing at the unit. Now one of the problems you can face is I'm now going to turn my hand sideways. You can see now and again you get a high reading. That's because my hand isn't directly in line with the sensor. And one of the things I tell you to do is, once you've got this sketch running, have a little bit of a play moving different objects in front of the sensor at different distances. It's quite useful to do this because then it gives you an idea of how the sensor is going to react to different types of objects. What's its sensitivity going to be like? Because again, it's one thing to bounce a signal off a great big wall 4 meters away. It's another thing to get a reading off a chair leg or a table leg, which of course is much smaller. So do some experiments and find out how the sensitivity works, and then certainly if you're building a sort of a robot car that's going to do obstacle avoidance, it then starts to give you an idea of at what distance this sensor will reliably be able to pick up the sort of obstacles that you want it to avoid. Now if we go back to the sketch as it's written, obviously I've tried to comment every line to explain what is going on, but the problem with this sketch at the moment is it's running in the main loop. But if you think about it, if we now wanted to start to control some motors, you know, we want the car to be changing direction, we can't because we're using delay. Now whenever you use delay, the Arduino basically goes into lockup mode for that period of time, and it will not receive inputs. You can't put any other code in here to do anything else. So it's that strange thing that I could find the distance, but until 1 second, 1000 milliseconds has gone by in this sketch, I wouldn't be able to change direction, which if I'm coming up to an obstacle at speed is going to be a bit of a disaster. And this is why in the next sketch that we look at, we're going to take all of this code and we're going to put it into a function that can be called whenever we want from wherever we want in our code. So let's load up the next sketch. So in this next sketch, just as in the first one, we've got our trigger pin and our echo pin. The reason I picked pins 6 and 7 is because if you're doing the robot car tutorial, we've already used sort of pins 8, 9, 10 and 11, I think it is. So I wanted to pick some pins that we hadn't used already. These pins could be sort of any digital pin that you want. Basically 2 and above are the best ones to be using. Then what we've got is a global variable called sensor timer 1. Now this is an unsigned long because we're going to be using it to measure time. Now if you've done the lesson on using delays and millis on the C++ lessons on the Digital Town site, it's lesson 7, you'll have learnt how this sort of code works. And what happens in the main loop is we have a timer. It takes a time, and then once the value of millis, which is the number of milliseconds since the Arduino was turned on, gets to a value that's above the sensor timer, then this if statement will trigger. What I immediately do here is I add another 1000 milliseconds to the value of the current time in millis, and we make that the sensor timer so that in 1 second's time millis will be greater than the sensor timer, and it'll keep going round in a loop. And this basically means that the sensor, instead of using a delay, is now triggering using a timer once a second. So it will trigger at the same rate, but the difference is that we could have lots more code written down here controlling motors or other items that will not be blocked by a delay. And that is the real advantage of using a timer that is controlled by millis. Now, once I've done that and we've decided we're going to trigger the sensor, you'll notice then that distance is calling a function called getDistance HC-SR04. And what it does is it sends the value for the trigger pin and the echo pin. Now you'll see why I've sent those in the following sketch, but this is the function. So we've got our function. It receives the value for the trigger pin, and it receives a value for the echo pin. You'll notice I've put a slightly different variable name in. That's because these are local variables that are only kept within this function. Again, we've got some more local variables here. So I've got an unsigned long for the duration, again the time for the echo, and I've got an integer called my distance. Now the code here is exactly the same as we've already seen. The only difference is that the pins have been changed to the value that I gave, what the variable name that was given when I declared the function. If you have done lesson 10 on using global and local variables on the Digital Town website, you'll understand what the difference is between a global and a local variable, but basically these values are just available during the lifetime of this function. So again, we take the trigger pin low, we wait 2 millionths of a second. Now you'll notice I said about the problems of using a delay in the main loop. Delay is not great, especially when you're using a delay of 1000 or 1 second. Now here we are using a delay which to a degree is locking up the Arduino, but because it's for only 2 millionths of a second, it's not going to have any impact on any other code, so it's safe to do it. And again here, when we're doing one for 10 millionths of a second, it's such a minute amount of time that it's really going to have no impact on the timing of anything else if we're building sort of an obstacle avoiding car. So we've got the same code, we've got the duration that comes from the pulse in, we've got the calculation, and then what it does is with the function, the return value that it sends from the function is the distance that we've calculated just as we've done before. The distance comes out down here, and then just as before we serial print. And to be honest, when you look over here at the serial monitor, there's really no difference at all. It functions in exactly the same way. However, the advantage that you would have is that this function call here could be moved anywhere within your code. It could be triggered by all sorts of different events that you could decide at will, and however you trigger it, it's always just going to call the function that you've already written and just give you the answer. So anywhere that you move this within your code will not affect what goes on here. So what we're going to do now, we've seen how to control one of these modules using the function. I'm now going to swap over the windows, and we're now going to look at some similar code, but we're going to be controlling 3 different sensors at the same time. So here's our third sketch, and very, very similar to what has gone on before, except you'll notice that when I've declared the trigger pin, if you remember before we were just using pins 6 and 7, what I've actually done in this case is I've also attached another set of pins to a second module using pins 5 and 4, and I've got a third module that's connected using pins 3 and 2. Again, the ground and the VCC, you just connect them to a common 5 volts and a common ground. The only pins that need to be separated out are the trigger pins and the echo pin. Then what I've done, just to display that these are 3 separate units being fired at their own times, instead of having sense timer 1, we've actually created 3 timers. This is very, very similar to one of the sketches that I did on the lesson 7, which was about delay versus millis and controlling timings in programs. So we've then got exactly the same function here to get the distance. I've made no modifications to that function whatsoever, and the only changes that I've made are in the setup, because obviously with the extra pins, those have had to be set up as an output and an input for each module. And then finally, when we go down to our loop, this code here is the code that was from the last sketch. Don't forget, if you get stuck with this, all of these sketches are all on the Digital Town website, so don't start to panic and think you've got to somehow learn this while the video is on. They're there for you to spend all afternoon, all day, as long as you want looking at them. So you've got this code here, and what it's saying is if the sensor timer 1 comes to its time, then get the distance by sending these 2 pins, which is for our first sensor, to get a distance. So sensor 1's distance, we've got a distance. Now what I've done, if you notice, I've changed the timing to 1600, 1.6 seconds. On this second one, sensor 2, I've set the timing to 1.5 seconds, and in fact on sensor 3 I've got it to 1.4. I just decided I'd use different timings because they could eventually overlap if you're interested. Now sensor 2 has its own timer that we declared further up, just as sensor 3 will. So this is working its own loop, and in this case, when the if statements is met, when millis is greater than sensor timer 2, this time it's going to call exactly the same function as the previous one, but instead of sending trigger pin and echo pin, it's going to send trigger pin 2 and echo pin 2. So what we're doing is sending different pin numbers through to the function, and the distance it will give is the distance that it gets by firing and receiving those pins. And exactly the same happens down here with the third loop. I've got trigger pin 3 and echo pin 3. So in each of these different ones we will see a different set of results. So I'm just going to compile this, send it up there. Hopefully again it's not going to be too long. I've connected up all of these different sensors to my Arduino board. Let's just hope all of this works. So we're there, program started, and then what I'm going to do is I'm going to try and put things in the way, and as you can see, all the values, hopefully that's it, all the values are changing as I'm moving my hands over the front of them. So there you have an example of how you control 3 different sensors using 3 separate different timers. Now that can be quite useful. Sometimes what you would do is you wouldn't use these all for one particular sensor. What we might do is we might have one function here controlling a servo, another could be controlling the sensor, something else could be controlling a motor. But again, it gives you an idea of how different things can all be controlled at the same time. Now what we're going to do to finish with is we're going to have a look at a far more sensible way of connecting 3 sensors together. I've connected them up in a way that I would use them in a car. So here we are with sketch number 4. Now again, we've got the pins that have been used. Nothing has changed since sketch 3. The sensor timer 1 is still there, but you'll notice sensor timers 2 and 3 have been removed. We don't need them for this sketch. And instead, I've created an integer called next sensor. And I've given it a start value of 0. We've then got our function that is calling the sensor, sending it 2 pins that we want it to work with. So the setup remains the same, the function remains the same, but what changes in this case is down in the main loop. So what I've done here, this time we've only got one timer, and this time the timer is going to fire off every half a second. Now I've done it that way because if you look over at the COM port as it is now, which is actually running this code, I can actually see that sensor 1, 2, 3, 1, 2, 3, it's working through the sensors one after another. If I was doing this on a car, I would probably change this to every 50 milliseconds because I'd want to be checking the distance far more often. But if I changed it to 50 milliseconds now, the text would be flying up the COM port window so fast that we wouldn't be able to read it. So I've slowed it down just for our sake. So what happens here? Well, we've got the if statement using a millis timer as normal. And then what happens is if millis is greater than sensor timer 1, we come in here and we've got a switch statement. And what we're doing is we're doing a switch on next sensor. Now we know that when we start that next sensor is going to have a value of 0. So the value for case 1 is not met. The value for case equals 2 is not met. But the value for default is met because it's not 1, it's not 2, it's something else. It's a 0. And so what I've done here in the default, I've said, okay, if it's 0, call the function using our trigger pin and echo pin. Get the distance and let us know what that distance is. Then what it does is it comes out of the switch statement and we add a value of 1, which is what happens here. Next sensor plus plus means that next sensor takes a value of 1 greater than its current value. Just as an extra bit here, you'll notice that what I've said is if next sensor becomes greater than 2, then next sensor becomes 0, because obviously if next sensor got to be greater than 2, it will always trigger the default because it's never going to be 1 or 2, and I want it to be working through all 3 sensors in sequence. So every time the value gets to greater than 2, it swaps it back to 0 and it starts the whole thing again. So what is then happening is every time the timer times out, every time millis is greater than the sensor timer, it will first of all send the first sensor value. Half a second later it will do the next sensor. Half a second later it's going to do sensor 3, and that's why when you look in the COM port over here, you can see that we're seeing sensor 1's value. Let's just stop it for a second. Sensor 1, sensor 2, sensor 3, sensor 1, sensor 2, sensor 3. And if I go back to the values moving again, if I start to stick my hands in front of these sensors, you can see them all beginning to change their values, as hopefully I get my hands in the right place. So what you're seeing here, combining the millis timer with a switch sensor, this might be the sort of thing where imagine your car is moving along. You've got 3 sensors on the front, or in fact let's think of a normal car. Let's imagine you're reversing your car. What will happen is it will trigger the first sensor, then the second sensor, then the third sensor in with very short time intervals between. If you think about it, if we're firing sounds out all over the place, we can't fire them all at the same time, because if we fired them all at exactly the same time, there is actually a danger that one sensor could receive the bounce sound from another sensor. So if you think about that on your car, if one sensor was picking up the rebound from another sensor, it would make an object appear to be further away from the car than it really is. So as your car's reversing in real life, those different sensors are probably firing off. I would imagine it might even be down to 5 millis between each trigger. Very, very short time periods, but they will be firing constantly in sequence. So if we're building a robot car, we could have one sensor pointing slightly to the left, one straight ahead, one slightly to the right, and by firing them all off, we would then be able to find which direction has the clearest route, and that will then allow us to send controls to our motor to change direction so that our obstacle avoiding car is then pointing in the direction that has no obstacles in the way. So that's the sort of thing that this type of code is used for. What you could even do is turn all of this into a separate function to move it out of the loop. Again, we'll probably do that in the robot car tutorial as we move on. But I just wanted you to be able to see how useful it is to have all of this code in a separate function, because it means that you can keep calling the same functions over and over again, and if you change the order of anything in here, it doesn't mess up any of the code within your function. So I hope this sort of lesson has been useful to you. We've sort of looked at the basics of this sensor. We've seen how to write a simple sketch for the Arduino. We've then turned it into a function that we can just call from anywhere in our code and move from one sketch to another. We've also seen how we can use that function to call multiple sensors at random time intervals, and then in the final sketch we've seen how to do it one after the other in a way that would be useful for an obstacle avoiding car with multiple sensors on it. A typical example, you might not just have a sensor on the front, you might have a sensor on the back. Again, by being able to call it in a function, you wouldn't want to bother calling the one on the back if you're moving forwards, but as soon as you change direction, you want to use the back one instead of the front one. So that's the idea behind the code that we've looked at today. I hope that you've enjoyed it, and if you have enjoyed it and you've got time, click the like and subscribe buttons. So see you in the next lesson.